So, in today's lecture, we will see the characterization techniques. We will see some of the characterization techniques. As we have seen in our previous lectures, we have seen certain characteristic techniques like XRD, X-ray diffraction, uh, transmission electron microscopy, scanning electron microscopy, atomic force microscopy, magnetic force microscopy, and scanning probe microscopy. Right. So these are some of the characterization techniques after the fabrication of nanomaterials, which we have studied in our previous lectures. So in today's lecture, we will see one of the characterization technique called STM. STM stands for scanning tunneling microscopy. Scanning tunneling microscopy. STM stands for scanning tunneling microscopy. Okay. So this is also one of the characterization techniques for the fabrication or characterization techniques to characterize the fabricated nanomaterials. Okay. So in this characterization technique called scanning and tunneling microscopy, here also unlike other microscopic techniques, here we will see the tunneling process. Right? So this tunneling phenomena is purely a quantum mechanical phenomena. So it's purely a quantum mechanical phenomena. That means the tunneling is unlike classical. Okay. So tunneling resembles this tunneling feature is one of the essential difference that we bring between classical phenomena and the classical phenomena. Right? So classically, if you see an object, suppose if there is an object, right? So classically, this particular object to come to other position, it needs to go like this. This is what we see classically, right? Whereas in quantum mechanical phenomena, so there is a process called tunneling. That means the same object when tunneled into that, right? So it can resemble outside here. Right. So this particular process is what we call it as tunneling. So tunneling is essential property of the electron. Electron has some dual properties, right? So like matter exists in dual nature, right? So matter exists in dual nature. One is wave nature, and is particle nature. So in that scenario, so this tunneling is one of the essential property for the electron to tunnel into the barrier, right? To tunnel into the barrier, so that the result will be very smooth and soft, right? So based on that particular phenomena, this particular characteristic technique is essentially based, right? So we'll see this particular characteristic technique. This is an instrument, right? So this instrument is used to characterize that particular fabricated nanomaterial, right? So nanomaterial nanostructure, right? So this is what the scanning tunneling microscopy is. So this is what this instrument is, right? So this is what the instrument, and this is what the tunneling. This is what the tunneling of electrons, the tunneling current of electrons. So this is what the tunneling current of electrons. This is what we call it as scanning tunneling microscopy. So this is a lot of instruments. This all need to be this instrument is to be fabricated. This instrument is to be fabricated in. This instrument is to be fabricated in totally the closed chamber, right? So closed chamber in a completely clean room. It should be based in 100 class clean room or 1000 class clean room. So based upon that area and equipment, we need to go for the clean room, and we can see that particular scanning tunneling microscopy, right? So this is what the tunneling of a current of electrons. So tunneling of electrons. So the basic contents that we'll see in this today's lecture is the history regarding the STM. We'll see what about the introduction behind this scanning tunneling microscopy, and we'll see some of the definitions of tunneling and all, right? And we'll go for the basic principle. What is the basic principle for the tunneling, right? And how the equipment is set up, and we obviously will go for the application. So this is the outline that we consider. So these are the main outlines or the contents of this particular lecture, right? So if you go to the history, so this was developed in the year 1981 by Gerd Binning and Heinrich Rohat at IBM, right? At IBM, that is a country, at IBM Zurich, right? So there's a country. So Zurich is a place where this particular instrument was developed, and it was later patented by IBM, International Business Mainframes, right? Business machines, mainframes. So it was this particular instrument was patented in the year 1982, developed in 1981 and patented in 82. And this particular instrument, so this Binning and Roher got the Nobel Prize, won the Nobel Prize in the year 1986. So this is what some of the histories, or this is what the achievement of atomic resolution. So resolution is what the atomic size, right? Atomic size, unlike in we have seen in scanning probe microscopy and atomic microscopy, the resolution that is incorporated here is the atomic resolution. And resolution that we can see, the size of the particle, size of the is can be up to 0.01 nanometers. And these are the two persons, right? So these are two Nobel Prize winners, scientists, Gerd Binning and Heinrich Roher, right? So this is what some of the history. So this was so silicon surface atoms were enlarged at 20 million times, color enhanced by computer, right? So the colors were enhanced by the computer programming simulation point. So the world's first images of individual surface atoms and the bonds that hold them in place were produced by research technique developed by IBM, that is what scanning tunneling microscopy. Right. So the world's first image of individual surface atoms and the bonds that hold them in place, were produced by IBM. So which is essential. It is essential for the scanning tunneling microscopy. So this is what the history. So first it was developed in 1981. Later patented in 1982, and people won the Nobel Prize for this particular great discovery. And the resolution of the particles can go up to 0.01 nanometers. Right. So if you see the introduction part. So scanning tunneling microscope is a powerful technique for viewing surfaces at the atomic level. So this is what the one powerful technique which is used for viewing the surfaces at the atomic level, right? So STM probes the density of states of material using tunneling current. So which is a very, very fundamental point, So STM probes. So here also the scanning tunneling microscope use the probes, right? So probes the density of states. So which is purely a quantum mechanical phenomena. That is what we write, the density of state dz equals to integral n f of z dz. This is a mathematical quantity, right? So which integrate, we obtain the density of states of a material. So density of state material, that is purely nanostate, right? So that is what quantum confinement exists from this. So once a quantum confinement coming to existence, then tunneling obviously comes in. The tunneling phenomena obviously comes from. So that's what STM probes the density of states of a material using tunneling current. So this STM is based on the concept of quantum tunneling, right? So quantum tunneling. So this is what the sample that is placed. This is what the sample, and the tip touches the surface of the sample, and we can see the resolution. We can see the atomic layer tunneling of electrons. So this is our tunneling. This is our tip. So electrons will tunnel into that and form the tunneling of electrons. So this is what generally observed here, right? So the STM is based on the concept of quantum tunneling, right? So STM probes the density of states of material using quantum tunneling current, right? So this is what some of the introductory facts, so which we need to understand. So scanning tunneling microscope is a powerful technique for viewing the surface at the atomic level, not at even nano level, atomic level. The STM proves the density of states of material using quantum tunneling current. The STM is based on the concept of tunneling, quantum tunneling, right? So this is one of the fundamental case, right? So this is the introductory part. So if you come to the general overview, an extremely fine conducting probe is held about an atom's diameter from the sample. Electrons tunnel between the surface and the tip, producing electrical signal. When it slowly scans across the surface, the tip is raised and lowered in order to keep the signal constant and maintain the distance. Right? So this enables it to flow even the smallest details of the surface it is scanning. So an extremely fine conducting probe is held about an atom's diameter from the sample. Electrons tunnel between the surface and the tip, producing an electric signal. While it slowly scans across the surface, the tip is raised and lowered in order to keep the signal constant and maintain the distance. So it enables to flow even the smallest details of the surface as it is scanning. So this is what the sample we have seen in the previous slide. So this is what the sample, the tip touches the sample and scanning of the electrons, scanning of the image will take place. So there we can see the tunneling of electrons. So this is what the tunneling of the electrons. This wave-like phenomena. This wave-like phenomena is what we can see as the tunneling of electrons, right? So this is a very important note that we need to understand. An STM does not measure nuclear position. Okay, nuclear position directly cannot be observed by using scanning tunneling microscopy. Rather, it measures the electron density. Clouds on the surface of the sample. on the surface of the sample. But in cases the electron clouds represent the electron clouds represent the atom locations pretty well, but not always. That's why STM does not measure the nuclear position directly. It does not measure the nuclear position directly. Rather, it measures the electron density clouds on the surface of the sample. Right? So indirectly, we can tell that it is also used to study the surface morphology. Surface morphology, as you have studied in a scanning electron microscopy, right? So that's what it measures the electron density clouds on the surface of the sample. So, but in some cases, the electron clouds represent the atom location pretty well, but not always. So, look, atom location can be found, but the atom location cannot always be found. It can always be found. So, this is very important note which we need to understand when we go for the characterization. So, when we do characterization of a nanostructure or a nano sample, right? Using the scanning tunneling microscopy. That's why we wrote it as an important note. So, as we told this quantum tunneling, as we have seen in the very first beginning part, so this is purely a quantum mechanical phenomena. So, unlike classical case, classical wave function for finite square well potential where the energy is very less than the potential, that is V. Classically, when an object hits a potential that it does not have enough energy to pass, it will never go to the potential wall. It always bounces back. That means when an object hits that, okay. So if it does not have enough. If this particular barrier does not have enough energy to pass, it will never go to that potential wall. It takes the reflective path, the bounces back, right? So in English, if you throw a ball at a wall, it will bounce back to you, right? Depending upon the position, depending upon the strength of the wall, right? So this is what the quantum tunneling case exists, from where the quantum tunneling exists, right? So quantum wave function for finite square well potential where V less than V. So here the energy is less than the potential, where here E is less than V. Okay, in quantum mechanics. But in quantum mechanics, when a particle hits a potential that does not have enough energy to pass, when inside the square well, the wave function dies off exponentially. That means it decays. So this is wave function that so this wave function dies off exponentially, right? Decays, right? Exponentially. If the well is short enough, there will be a probability of finding the particle on the other side. Short enough, depending upon the size. If you say here, if you see here, the size here. So size can be observed, right? So in quantum mechanics, when a particle hits a potential that does not have enough energy to pass, when inside the square well, the wave function dies off exponentially. If the well is short enough, there will be a noticeable probability of finding the particle on the other side. So quantum tunneling, the finite square well potential is a good approximation for looking at the electrons on conducting slab with a gap between them. So this is what we understand. The phenomena of quantum tunneling, right? So see here, if the wall is strong enough, so it funnels the particular tunnels, and slowly the potential becomes zero. That means slowly it decays, right? Right. So the conducting slabs with the gap between. This is one of the cases of quantum tunneling phenomena which we need to understand. So now, what is this tunneling? How this tunneling is incorporated? What is this tunneling in scanning tunneling microscopy? When a conducting tip is brought near to the specimen or near to a metallic or semiconducting surface, a bias between the two can allow electrons to tunnel through the vacuum between them, right? When a conducting tip is brought very near to metallic or semiconducting surface, right, a potential between the two can allow electrons to tunnel through the vacuum between them. So in order to understand this tunneling effect, we need to talk about the density of states. So that is which a fundamental case. It is a fundamental case, as we told. Density of states is a fundamental case for the existence of tunneling. That is what we call it as quantum confinement. When we speak about quantum confinement in nano, right, nano for the atomic dimension, we need to speak about this particular quantum tunneling effect. We need to talk about the density of states. Now, what is this density of states? So electron in an isolated atom live at specific discrete energy levels, right? That means energy is quantized. That is what we are telling about. Quantum confinement, that is energy quantization, E equals to n h square by 8mL square. right? Or we can write E is equal to energy is quantized, that is E equals to N E1, right? So this is that energy is quantized, energy quantum confined, N square pi square S square by L square, right? So this is what we speak about the energy confinement. That means energy is quantized. Energy is quantized. So electrons in an isolated atom live at specific discrete energy levels. In case of metals, the levels are so close together that instead to list energy levels of all the electrons, we can say interval the density of state around the energy E. So this is what we speak about the Fermi level and the sample Fermi level and energy, right? So Fermi level is a level. Fermi level is the highest energy level occupied by the electron, right? Fermi level, which we call it as EF. So Fermi energy, it is the highest energy. It is the highest energy occupied by the electron. Highest energy occupied by the electron at T equals to 0 Kelvin. So that particular level is what we call as Fermi level. Fermi level is the highest energy occupied by the electron at T equals to 0 Kelvin, right? When we speak about Kelvin state, so we tell that Fermi level is the highest energy level which is occupied at highest energy, right? So here we have this sample specimen, right? And these are all the electrons, and this is your Fermi level, this is energy. So we can see here, so this is your E energy, so Fermi energy is E and EF, and this is the energy. So where we write about the Fermi-Dirac distribution function, because when we speak about the density of states, when we speak about the density of states, the fundamental case that exists is the Fermi-Dirac distribution function. This Fermi-Dirac distribution function in mathematically can be written as f of E equals to 1 by 1 plus exponential of E minus EF by KT. So when we speak about the density of state, people need to understand the fundamentally what is the Fermi-Dirac distribution function. That is f of E equals to 1 by 1 plus exponential of E minus EF by KT. So here E resembles energy, EF represents the Fermi level. So when we start about this, so the Fermi-Dirac distribution function f of E, so f of E is also one of the essential condition to find the density of state. That's why when we derive the equation for density of state, so the quantum confinement, we write dn equals to integral E plus dE, E to E plus dE, right? E to E plus dE, n of E, f of E, z of E, right? Z of E into d. So where we go for the conditions of derivation, right? Where f of E resembles the Fermi-Dirac distribution function and the equations for different states. So that's why the density of state and energy E, the density of states dYs E is the number of electrons sitting in the strip, which is denoted by delta E. So this is very fundamental cause in scanning tunneling microscopy. So the electrons fill up the energy valley in the sample until there are no more electrons, right? The top energy level at which electrons sit is called the Fermi level. That is what we write as EF. So that is what we are telling. EF is equals to, here it's the same expression, 1 by EF equals to 1 by a exponential of E minus EF by KT, right? Which is called the Fermi energy level. For every energy E, the density of states is the number of states sitting with the density of E divided by D. So this is what the density of states. So that is what we write n equals to integral E to Z plus E plus dE. E plus dE in the energy level E plus dE f of E ZED. So this is what the condition is, right? So this is a vacuum barrier, right? Vacuum barrier. The electrons in the tip and the sample are sitting in the two separate levels, separated by a heavy, which is a vacuum chamber, right? So this is your vacuum chamber, and this is your Fermi level, tip and sample, work function, and EF plus delta E. That is what we see. So this is what the vacuum barrier is. So this is how the electron tunnel takes place. So the electron sample here, we have the EF plus delta E or EF plus phi, right? So this is the bias voltage and the turning electron, and this is what the tip is. Right. So by applying the bias voltage to the sample with respect to the tip, we effectively raise the Fermi level of the sample with respect to the tip. Now we have empty states available for tunneling into. So the quantum tunneling, now we look more into depth at the case of tunneling from one metal to another. EF represents the Fermi energy, as we told, creating a voltage drop between the two metals that allows current. So we have N of Z and we have EF. So this is what the voltage tip that is generated. This is what the metal variation. This is what the metal variation. This is sample and this is the tip. So between the tip and sample, some current is generated to the tunneling cave, so where the bias voltage is required. So the expression to the barrier, the quantum mechanics predicts the wave function dies off exponentially. So that's why we write psi of d equals to psi of psi naught e power minus kd, where k equals to under root of 2m into 5 minus e by h. So the probability of finding an electron after a barrier of width d is w of d equals to probability density mod of the side d square is equals to psi naught square e power minus 2 kd, and I equals to f of e power minus 2 kd, where f of e is a Fermi function which contains a big the local density states. This is a material property obtained which is obtained by measurement. So quantum tunneling case is given by I is proportional d power minus 2 kd, where k is approximately under root 2m phi by h. Plugging in typical values for mass d and phi, where phi is the average work function of the tip and the sample at density changes, the distance changes by 1 angstrom, the current changes by a factor of about 10. So if you bring the tip close enough to the surface, you can create a tunneling current even though there is a break in the circuit. The size of the gap is practiced with the order of 10 power minus 10 angstroms a couple, right? As you can see, the current is very sensitive to the gap of distance. So this is what the basics of STM is, right? The tunneling current as a measure of surface characteristics, sharp probe and prepared surface of sample, and bringing them close around 4 to 7 angstroms. So bias voltage is around 1 volt, results in the tunneling, which is I equals to 0, used in ultra high frequency waves, ultra high frequency value. Current is very sensitive to the gap between the tip and the surface, right? So this is what the bias voltage, and the distance is around 6 angstroms. So bias voltage ranges from millivolts to the volt. Why such a fine tip is required? So this is what the second tip shows above is resisted by about 2 atoms, and thus carries about a million times less current. That is why we want such a fine tip. If we can get a single atom at the tip, the vast majority of the current will run through it and give us the atomic resolution. So this is how the setup is maintained in the laboratory. So we use some interfacing and data processing and display. This is how you can see this. We have distance control and scanning unit. We have tunneling current amplifier, current voltage for piezoelectric tube. This is what the tunneling voltages we have. Okay, tunneling voltage and the sample specimen where is need to kept, and the tip interacts with the sample, and we can see the imaging here, right? So this is what the imaging fact we can see here. So instrumentation, the sensors that we use are piezoelectric transducers used for control movement in XYZ axis around plus or minus 0.05 angstroms. It's a coarse positioner, mechanism for vibration oscillation, so coil springs and magnetic damper, noise cancellation, final image enhanced through image processing, feedback control used for height adjustment. Okay, so the probe, so tungsten wire is etching material, platinum, indium, sharing or gold, extremely sharp probe, 1 atom thick, resolution depends on the radius of curvature of tip. Blunt probe creates images distortion. So this is what the image. So this is what the signal we can see here. So we can see the imaging process, right? So here the tunneling of rays we can see, right? So this is around 100 micrometers, and this is 10 micrometers, and this is 1 micrometer. So this STM tip automatically sharp needle and terminates in a single atom pure metals alloys, and you can go for a chemically modified conductors, right? Chemically modified conductor. So, so the preparation of tips cut by a wire cutter and is used as a cut followed by electrochemical etching, right? So these are how the tips are fabricated, right? So preparation of tips, we use pure metals and alloys, platinum, rhodium, and platinum iridium, or the metal alloys which we use. Alloy, we know that is a combination of 2 different metals, right? So pure metals like gold and lead and all. Okay. So the small movement and fast movements to get the distance between the tip and the sample down to a couple of angstrom, where the tunneling current is at measurable level. STMs use feedback servo loops and converse piezoelectricity. Servos are small devices with a shaft that can be precisely controlled with electrical signals. Servos are used all the time in radio-controlled cars, puppets, and robots. So converse piezoelectricity. Piezoelectricity is the ability of certain crystals to produce a voltage when subjected to mechanical stress. When you apply electric field to piezoelectric crystal, the crystal distorts, and this is known as converse piezoelectricity. The distortion of piezo is usually on the order of micrometers, which is in the scale needed to keep the tip of the STM a couple angstroms from the surface. So where the electric field is generated, and the tip we have the electric field, right, and piezos, okay, and the tip. Okay, so we can see that. So vibration oscillation, right? The original STM designs have the tunnel unit with permanent magnets levitated on a superconducting lead ball. They use around 20 liters of liquid helium per hour. Liquid helium you need to pour. Liquid helium per hour. So vibration is a simple and presently widely used vibration protection with a stack of metal plates separated by Viton and ultra high vacuum compatible rubber spacer. So these are some of the problems and solutions. So bringing the tip close to the surface and scanning of the fire feedbacks are overlooked. Keeping the tip close to the surface, this is a converse piezoelectricity, creating a very fine tip. Electrochemical etching forces between the tip and the sample negligible in most cases. Mechanical vibrations and acoustic noise, soft suspension of the microscope within a ultra high vacuum chamber, and thermal length fluctuations of the sample, and especially the tip, which is maintained at very low temperature, right? Very low temperature. The sample has to be able to conduct electricity, right? So this is how the working takes place. So this is how the working takes place, and we have the imaging process here. This is what the imaging, and this is what the working phenomena that takes place, and this is what the topography of the sample, and tip exposition, tip point position is a three-dimensional case. Okay. So this is what the position. This is what the sample layer we can study. That is in nanometers and nanometers. This is what the imaging can be done, and this is electrical equipment. This is what the working takes place. Okay. So these are the modes of operation: constant high mode operation, constant current mode of operation. So in constant high, variation of current with lateral distances, surface of a density of state, faster the scanning rate. Constant current feedback adjusts the height to make the current constant, surfaces of constant density of states, right? So this is what the image is interpreted. Gives the density of state of surfaces, the density of states, the number of electronic states per unit volume per unit energy. For a large scale energy, that is what the topography. So that's why density of states is nothing but we need to go for the volume, right? Volume per unit energy. So this is the hydrogen on gadolinium. So this is what the same image you can see, the hydrogen on gadolinium. So this is one of the image interpretation. So what are the advantages? High resolution images, the atomic scale, low power application, no damage to the sample. Sample is very secure. And disadvantage, need for high vacuum, as I told in the very first point. It needs a lot of high vacuum, so it should be maintained in a clean room. And samples limited to conductors and semiconductors only. Okay, they are not used for any type of ferromagnetic material. Okay. So high equipment cost, surface preparation, maintaining the tool sharpness. Okay, so equipment is very cost. Okay, so this is only for conductors and semiconductors. So this is purely for electrical applications. Okay, not used for magnetic materials. So application: surface, semiconductor surface structure, nanotechnology, superconductors, etc. Surface topography, atomic resolution, spectroscopy of single atoms. Okay? So image of reconstruction on a clean gold surface. Okay? Right. So typical applications of STM, right? So these are some of the applications. Powerful imaging tool, directly visualize electrochemical process in situ and in real space at molecular or atomic levels. Such interfacial electrochemical studies have been dramatically expanded over the past decade, covering areas in electrode surfaces, metal deposition, charge transfer, potential dependent surface morphology, corrosion, batteries, semiconductors, and nanofabrication. So these are some of the applications. Events in the EC data, electrochemical data, correlate with the changes in the topography of the sample. So these are some of the typical applications of STM. So metal deposition, when applying an potential negative of the equilibrium potential ER to cathode, bulk deposition of metal takes place. Nucleation and growth process. So deposition of metal preferentially occurs at the surface defects such as steps or speed dislocation. So this is the STM images of gold at 111 plane. Surfaces of 5 milli of MH2, 5 mH of H2SO4 plus copper. The bare gold surface is automatically plate terrace separated by 3 monatomic high steps. After a potential step to negative value, deposition of bulk copper occurs almost preferentially at the monoatomic high steps, namely the growing copper structures are decorating the gold surfaces. So this is what the STM based electrochemical nanotechnology, STM tip, EC STM tip crash method, jump to contact method. So these are the different STM based electrochemical technology, right? So this is a tool of manipulating individual atoms or molecules on substrate surface and directly them continuously to predetermined positions. So generated entities are clearly larger than single atoms due to their low stability to survive electrochemical environment at room temperature. So tip crash method, surface damage, use the tip to create a surface defect which then acted as a nucleation center for the metal deposition at pre-selected positions. So other method is jump to contact method. This is surface undamaged metal is first deposited on the tip from electrolyte. The metal loaded tip approaches the surface to form a pulsar voltage. The neck breaks, leaving a metal cluster on the substrate. Continued metal deposition on the tip supplies enough material for the next cluster generation. So this is what the STM tip, and this is what the surface is a metal cluster. Okay, so these are some of the STM based electrochemical nanotechnology. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.